Somewhere in the darkness between stars, something is wrong. Not wrong in the way that scientists usually mean when they say that, not the polite academic kind of wrong that fills conference rooms with careful debate and footnoted disagreements. This is a different kind of wrong, the kind that makes researchers go quiet in the middle of a sentence, the kind that shows up in data and gets stared at for hours because no one can figure out how to explain it without dismantling something they've spent their entire career believing. At the centre of our galaxy, 26,000 light-years away from where you're sitting right now, there is a place that should not exist the way it does, and the closer we look, the stranger it gets. We've known for decades that the Milky Way has a supermassive black hole at its heart. We gave it a name, Sagittarius A star, and we spent years proving it was there, tracking stars as they orbited something invisible and impossibly massive, watching light bend around a gravitational drain so extreme that not even light itself escapes once it crosses the line. In 2022, we finally photographed it. We saw the shadow of the event horizon, the glowing ring of superheated gas, the darkness at the centre, and for a moment it felt like we'd answered the question. We hadn't. We'd opened a door we didn't know was there, and behind it were rooms full of things we don't understand. Because here's what's actually happening at the centre of our galaxy, and why some of the most careful, most rigorous, most skeptical scientists on the planet are starting to say, quietly, in papers and conference halls and late-night conversations, that something is fundamentally off about everything we think we know. The galactic centre is not behaving the way it should. Stars are orbiting in ways that violate predictions. Gas clouds are surviving encounters that should have destroyed them. Energy is appearing where it has no business appearing. Structures are forming that have no explanation in any current model. And underneath all of it, there's a signal, faint, persistent, maddeningly consistent, that some physicists believe could be the first real evidence of something we've theorized about for 100 years but never actually seen. Dark matter, or something worse. This is the story of what's at the centre of our galaxy, why it's breaking our best theories, and why the scientists who study it most closely are starting to wonder if they've been looking at the universe the wrong way this entire time. Chapter 1. The Black Hole. We finally saw. Let's start with what we know, or at least what we thought we knew. Sagittarius A star, pronounced Sagittarius A star, sits at the rotational centre of the Milky Way. It has a mass of approximately 4 million times the mass of our Sun. If you took 4 million suns and compressed them into a single point in space, you'd have something approaching what's at the centre of our galaxy. The gravitational field it generates is so powerful that stars orbit it at speeds that would seem impossible if you watched them from here. We didn't always know it was there. For most of human history, the galactic centre was just a direction, a bright patch in the night sky in the constellation Sagittarius, thick with stars and dust, and the kind of visual chaos that makes it hard to see what's actually happening. The dust was the problem. The galactic centre is hidden behind so much interstellar material that visible light can't get through. It's like trying to see something that's behind 50 walls, but radio waves can get through. And in 1974, astronomers Bruce Ballack and Robert Brown, working with the Very Large Array Radio Telescope in New Mexico, detected something unusual at the centre of the galaxy. A compact, incredibly bright radio source that didn't move the way everything else moved. They named it Sagittarius A star, the asterisk in the name being a notation used in atomic physics to indicate an excited state. A kind of inside joke that has aged remarkably well, given how excited the source has turned out to be. For years, the nature of Sagittarius A star was debated. Was it a black hole? A very dense cluster of stars? Something else entirely? The evidence pointed toward a black hole, but evidence pointing and evidence proving are two different things. The proof came from watching stars. Starting in the 1990s, two independent teams of astronomers, one led by Reinhard Genzel at the Max Planck Institute in Germany, and one led by Andrea Ghez at UCLA, began a project that required almost supernatural patience. They pointed their telescopes at the galactic centre, and they watched. Year after year, they tracked individual stars in the dense cluster surrounding the central radio source, measuring their positions with extraordinary precision. What they found was astonishing. The stars near the centre were moving in elliptical orbits, real, closed, gravitationally bound orbits, around a point in space where Sagittarius A star sat. and not just slow, lazy orbits. One star, designated S2, or SO2 in some naming conventions, was completing a full orbit in just 16 years. At its closest approach to the central point, an event called periapsis, it was travelling at nearly 3% of the speed of light. 3% of the speed of light, around something invisible. The only object known to physics that could generate that kind of gravitational pull from such a compact region, while emitting so little light, was a supermassive black hole. The math was unambiguous. The mass had to be concentrated in a region smaller than our solar system, and it had to be around 4 million solar masses. Anything other than a black hole would have collapsed under its own gravity long ago. Genzel and Ghez shared the Nobel Prize in Physics in 2020 for this work. The citation described it as the discovery of a supermassive compact object at the centre of our galaxy. It was one of the most elegant pieces of observational astronomy ever conducted. Decades of patient watching, of tracking light across impossible distances, of reducing uncertainty measurement by careful measurement until the conclusion became unavoidable. Then, 2 years later, the Event Horizon Telescope collaboration released the image. The EHT is not a single telescope. It's an array of radio telescopes distributed across the Earth, in Chile, Hawaii, Spain, Greenland, Antarctica, and elsewhere, that are synchronized so precisely that they effectively function as a single telescope the size of the planet. The angular resolution this achieves is extraordinary. It's roughly equivalent to being able to read a newspaper in New York from a cafe in Paris. Pointing this planetary instrument at Sagittarius A star and integrating observations over multiple nights, the collaboration produced the first image of our galaxy's central black hole. It looks in a way like what you might expect, a bright fuzzy ring of glowing orange-gold gas surrounding a darker central region. The shadow of the event horizon, the place where gravity wins. It was beautiful. It was confirmation of everything we'd believed, and it was, in a very real sense, the beginning of the problem. Because when you take the first clear image of something you've been theorizing about for decades, you also get the first clear look at all the things that don't fit the theory. And at the galactic center, there are a lot of things that don't fit. The image itself raised immediate questions. Sagittarius A star flickers. During the observations, the brightness of the emitting gas changed on timescales of minutes, far faster than models had predicted. The gas around the black hole wasn't behaving like a steady, predictable accretion disk. It was dynamic, chaotic, pulsing in ways that the simulations kept struggling to reproduce. The team ran hundreds of thousands of hours of supercomputer simulations to find models that matched what they were seeing. Many of them didn't. That flickering, that variability, would turn out to be one of many anomalies clustering around the center of our galaxy, like storm clouds around a mountain peak. And unlike the clouds, these anomalies don't dissipate when you look at them more carefully. They get darker. Chapter 2. The stars that should not orbit this way. Here's where it starts to get uncomfortable. Remember the stars that Genzel and Ghez tracked to prove the existence of Sagittarius A star? There are hundreds of them in the central parsec, the region within about 3 light years of the black hole. They're called the S stars, and they've been studied obsessively, because if you want to understand the black hole, you study what orbits it. What astronomers found, as they catalogued these stars in increasing detail, was that many of them are the wrong kind of stars. The galactic center is an extraordinarily hostile environment. The radiation environment alone, generated by the black hole's activity and the dense population of massive stars in the surrounding region, should prevent new stars from forming nearby. The tidal forces from Sagittarius A star are so strong that they should shred molecular clouds before they can collapse under their own gravity. Star formation requires regions of relatively quiet, dense gas, and the galactic center is about as far from relatively quiet as a place can get. Yet many of the S stars are young, disturbingly young. We're talking stars that are only a few million years old, essentially infants in astronomical terms, orbiting right next to a supermassive black hole that should have made their formation impossible. Astronomers call this the paradox of youth, and it's been known for decades. Various explanations have been proposed. Maybe the stars formed farther out and migrated inward. Maybe they formed in the disk of gas that sometimes surrounds the black hole during active phases. Maybe there's some mechanism of star formation we don't understand that works differently in high tidal environments. All of these explanations have problems. Migration would require losing orbital energy through interactions that should scatter stars out of the plane, not preserve their tight, regular orbits. Formation in an accretion disk has difficulties explaining the observed distribution of orbits, and invoking unknown physics is always a last resort in science, not because it's impossible, but because it's too easy to say, "We don't understand this mechanism," and stop looking. The paradox of youth is still not resolved. It sits in the literature, acknowledged and unexplained, a persistent bruise on our understanding of the galactic centre. But the orbital anomalies go deeper than just which stars are there. They extend to how those stars move. General relativity, Einstein's theory of gravity, makes extremely precise predictions about how objects move in strong gravitational fields. One of those predictions is a phenomenon called relativistic precession. An orbit in a strong gravitational field isn't a perfect ellipse that closes on itself. Instead, the ellipse rotates over time. The point of closest approach to the central mass shifts slightly with each orbit. The orbit precesses. For our solar system, this precession was one of the first great confirmations of general relativity, explaining an anomaly in Mercury's orbit that Newtonian gravity couldn't account for. Near Sagittarius, a star, the gravitational field is vastly stronger, and the precession should be vastly more pronounced. And indeed, in 2020, the gravity collaboration, using a system of interferometrically combined telescopes in Chile, detected the precession of the star S2's orbit around Sagittarius A star. This was a triumph. A direct measurement of general relativistic effects in the strong gravity regime near a supermassive black hole. The measured precession matched general relativity's prediction. But, and this is a significant but, the precision of that measurement opened up a new space of possible anomalies. When you measure something precisely enough to confirm a theory, you also measure it precisely enough to detect deviations from that theory. And as the measurements have gotten better, hints of small deviations have begun appearing in the orbital data. These aren't dramatic departures from general relativity. We're not talking about stars flying off in impossible directions. We're talking about residuals, small differences between the measured positions and the positions predicted by the best models. Residuals that are in some cases larger than they should be. Residuals that don't go away when you improve the data. Now, residuals can come from many sources: measurement error, unmodelled perturbations from other stars, small amounts of extended mass, gas, dust, stellar remnants, distributed through the region that could slightly perturb the orbits. Researchers have carefully tried to account for all of these. The residuals persist. One possible explanation is that there is an extended distribution of mass in the galactic centre. Not just the black hole, but a dark mass spread through the surrounding region that tugs on the stars in ways the models haven't accounted for. This dark mass could be stellar remnants, neutron stars, stellar mass black, holes, white dwarfs, objects left behind by generations of massive stars that lived and died in the dense galactic centre. Or it could be something else, something that doesn't emit light and doesn't interact with anything except gravity, something whose presence would explain not just the orbital anomalies near Sagittarius, a star, but also a much larger, much older, much more vexing problem that stretches across the entire galaxy. But we'll get to that. Chapter 3. Gas Clouds That Won't Die. In 2011, a team of astronomers led by Stefan Gillison at the Max Planck Institute announced the discovery of something unusual, a cloud of gas, designated G2, that appeared to be on a trajectory that would bring it extraordinarily close to Sagittarius A star. Close enough, according to their calculations, to be disrupted, torn apart by the tidal forces of the black hole and pulled into the accretion zone. The astronomical community paid close attention. This was a rare opportunity. Watching a gas cloud get disrupted by a supermassive black hole would provide direct observational evidence of the feeding process, the mechanism by which black holes grow. Models predicted that as G2 approached periapsis, its closest point to the black hole, it would be shredded and stretched into a long, thin stream of gas, part of which would be captured and heated, potentially triggering a burst of activity from Sagittarius A star. Periapsis arrived in 2014. G2 survived. Not just survived, passed through periapsis mostly intact. There was some distortion, some stretching, some tidal interaction. But the cloud that emerged from the encounter was recognisably the same cloud that had gone in. The predicted disruption did not happen. This was a significant surprise. The models had been reasonably clear about what should happen to a gas cloud with G2's estimated density and structure when it passed that close to a 4 million solar mass black hole. They were wrong. Several explanations were proposed. Maybe G2 wasn't a gas cloud at all. Maybe it was a star surrounded by a gas envelope, and the star provided a gravitational anchor that kept the structure together. Maybe G2 was the result of a stellar merger, two stars that had collided and produced a puffed-up gas-wrapped object that looked like a pure gas cloud but had a stellar core. These explanations might be correct, but they also raise new questions because G2 is not alone. In the years since G2's discovery, astronomers have identified several more objects in the galactic center region that share similar properties: compact, reddish, gas and dust enshrouded objects that move on highly elliptical orbits around Sagittarius A star. They've been designated G1, G3, G4, G5 and G6. Some of them have already made their close approaches to the black hole. None of them have been cleanly disrupted in the way the models predict. The group of objects has been named G-objects, or colloquially weird objects, and they represent a category of astronomical entity that nobody fully understands. They may be a new class of object, stars with very extended gas and dust envelopes, or the results of stellar mergers, or something else entirely. Their orbits suggest they may have formed in the same event, perhaps a past period of enhanced activity at the galactic center, but the timeline doesn't fit neatly with any known episode of Sagittarius, a star's history. What's especially strange is the orbits themselves. Many of the G-objects move on orbits that are tilted relative to the main stellar disk of the galactic center. Their orbital orientations are diverse, apparently random, when you'd expect objects formed in the same environment to share similar orbital characteristics. This randomness suggests either that the objects were scattered into their current orbits by some energetic event, or that the environment they formed in was far more chaotic than any current model can explain. There's also the question of what the G-object's survival tells us about the immediate environment of Sagittarius A star. If clouds of gas can make close approaches to the black hole and survive, that implies either that the tidal field near the black hole is somehow weaker than expected, which is difficult to explain given the well-measured mass of Sagittarius A star, or that the gas structures are more self-gravitating than they appear, or that there's some physical mechanism operating in the galactic center, environment that we're not accounting for. The simplest answer, that these objects have stellar cores, is possible but not confirmed for all of them. And even if it's true for all the G-objects currently known, it raises its own question. Why are there so many stars with such unusually extended gas envelopes clustering near the galactic center? What is producing them? What is maintaining them in an environment as energetically hostile as this? We don't know, and while we're sitting with that uncertainty, the galactic center has more mysteries waiting. Chapter 4. The Fermi Bubbles and the Energy That Came From Nowhere. Step back from the immediate vicinity of Sagittarius, a star, and look at the galaxy from the outside. Not from 26,000 light-years away, from much farther. Far enough to see the whole structure at once. If you could do that, and if you had eyes sensitive to gamma rays, you would see something extraordinary. Two enormous lobes of high-energy radiation, one above and one below the plane of the Milky Way, each stretching about 25,000 light-years in length. They're symmetrical, roughly spherical in cross-section, and they're glowing with gamma-ray energy that has no obvious source. These are the Fermi Bubbles, discovered in 2010 using data from NASA's Fermi Gamma Ray Space Telescope. They're among the most dramatic structures in our galaxy, and they emerge from the data like a ghost that everyone had been standing next to without noticing. The Fermi Bubbles are problematic for several reasons. The first problem is their energy content. The gamma-ray luminosity of the bubbles is enormous, roughly 10 to the power of 37 watts, sustained over their full extent. Generating that much energy requires a source that is, to put it gently, difficult to explain within our normal understanding of the galactic center. Something put this energy into the interstellar medium, and it put in a staggering amount of it. The leading candidates for the source of the Fermi Bubbles fall into two categories: past activity from Sagittarius A star, and galactic-scale outflows driven by a burst of star formation in the galactic center region. The galactic wind hypothesis suggests that at some point in the past, the galactic center experienced an episode of intense star formation, a starburst, that produced so many massive short-lived stars that their combined stellar winds and supernova explosions drove a powerful outflow of gas. This outflow would have inflated the bubble structures over millions of years, and the interaction of the outflowing gas with cosmic rays could generate the observed gamma-ray emission. The Sagittarius A star hypothesis suggests that the black hole was once much more active than it is today. In its active phase, it would have been classified as a quasar or active galactic nucleus, a bright, powerful engine of radiation driven by matter falling rapidly into the black hole. The energy released during this active phase could have inflated the bubbles. Some researchers have proposed that Sagittarius A star experienced a major active episode approximately 2 to 4 million years ago, which would be consistent with the estimated age of the bubble structures. Both hypotheses have supporting evidence. Both have significant problems. The starburst model struggles to account for the sharp, well-defined edges of the Fermi bubbles. If you inflate a bubble with a distributed wind over millions of years, you expect the edges to be gradual, fuzzy, a smooth transition between the high-energy interior and the surrounding medium. The Fermi bubbles have edges that are remarkably sharp. They look more like the result of a relatively sudden, powerful event than a slow, prolonged wind. The Sagittarius A star model struggles with timing and with Sagittarius A star's current quiescence. Today, the galactic center black hole is extraordinarily dim, one of the least luminous supermassive black holes relative to its mass that we know of. The ratio of its current luminosity to the maximum luminosity it could theoretically achieve, called the Eddington luminosity, is something like 10 to the power of -9. It's essentially asleep. For it to have produced enough energy to inflate the Fermi bubbles, it would have had to be luminous at or near its Eddington limit, essentially roaring at full power, and then gone almost completely quiet. That transition from maximal activity to near total quiescence in just a few million years is hard to explain. There are hybrid models that invoke both processes. There are models that invoke the outflow of cosmic rays accelerated by processes we don't fully understand. There are models that point to the nuclear wind driven by the combined activity of the dense cluster of massive stars at the galactic center without requiring a starburst. None of them fully reproduce all the observed properties of the bubbles. And then, in 2020, another telescope added a new complication. Germany's Ehrosita X-ray telescope, during its all-sky survey, detected structures now called the Ehrosita bubbles, even larger counterparts to the Fermi bubbles, extending roughly 45,000 light-years above and below the galactic plane and glowing in X-ray wavelengths. The Ehrosita bubbles encompass the Fermi bubbles but are significantly larger, and they appear to trace the outer shockwave of whatever event produced the inner structures. The Ehrosita bubbles imply an energy release from the galactic center that was even more prodigious than the Fermi bubbles alone suggested. We're talking about an event, or series of events, that reshaped the structure of the Milky Way on scales of tens of thousands of light-years. An explosion, in some sense, though one that played out over millions of years. What was it? We don't know. And that uncertainty about an event energetic enough to visibly restructure our entire galaxy might actually be one of the less disturbing mysteries at the galactic center, because at least the Fermi bubbles are things we can see. The thing that some scientists are most quietly worried about is something we haven't detected directly. Something that may be invisible by nature, that leaves traces not by its presence, but by the gravitational pull it exerts on everything around it. Something whose signal keeps appearing in the data from the galactic center, no matter how carefully researchers try to explain it away. Chapter 5. The Signal. In 2014, a paper was published in the journal Physical Review D that caused a quiet but significant stir in the physics community. The authors, Dan Hooper of the Fermi National Accelerator Laboratory and Lisa Goodenough, described an excess of gamma-ray emissions centered on the galactic center that couldn't be explained by any known astrophysical source. The excess had a very specific spectral shape. It peaked at energies around a few giga-electron volts and fell off on either side in a way that was highly suggestive. Suggestive of what? Of dark matter annihilation. Dark matter is the name we give to whatever is providing roughly 85% of the gravitational mass in the universe without emitting, absorbing, or reflecting any light. We know it exists because without it, galaxies don't rotate the way they should, galaxy clusters don't hold together the way they should, and the large-scale structure of the universe doesn't form the way the models predict. Something is providing that gravitational influence. It's not stars, it's not gas, it's not any form of normal matter we've ever detected. One of the leading candidate explanations for dark matter is a class of hypothetical particles called WIMPs, weakly interacting massive particles. WIMPs would have been produced in the early universe, would interact with normal matter only through gravity and the weak nuclear force, and would be essentially invisible to conventional detection methods. But in regions of high dark matter density, like the centre of a galaxy, where dark matter should concentrate under its own gravity, WIMPs would occasionally collide with each other and annihilate, and when they annihilate, they would produce, among other things, gamma rays, not just any gamma rays with a very specific spectral signature determined by the WIMP mass and the annihilation products. The galactic center gamma ray excess, now usually called the GCE, looks, in its spectral shape and spatial distribution, exactly like what you'd expect from dark matter annihilation via WIMPs, with a mass of around 30 to 50 giga-electron volts. This is not a vague resemblance, this is a disturbingly precise match. The signal has been studied intensively since Hooper and Goodenough's original report. It has been confirmed by multiple independent groups using different analysis methods. It persists at high statistical significance. It is spherically symmetric around the galactic center, which is exactly what dark matter annihilation would predict. Its spatial profile follows what's called a Navarro-Frank-White profile, the distribution that dark matter halos are expected to have based on cosmological simulations. So why aren't scientists celebrating the discovery of dark matter? Because there are alternative explanations, and because dark matter discovery is one of the most consequential possible scientific claims, and extraordinary claims require extraordinary evidence, and the current evidence is not quite extraordinary enough. The main competing explanation for the GCE is a population of millisecond pulsars, rapidly rotating neutron stars that emit gamma rays. Millisecond pulsars are known to produce gamma ray emission in the energy range of the GCE, and the galactic center is a dense stellar environment where you'd expect an elevated population of neutron stars. If there's a large, as yet unresolved population of millisecond pulsars in the galactic center, their combined emission could produce something that looks like the GCE. This explanation has its own problems. The expected number of millisecond pulsars needed to explain the entire GCE is very large, much larger than current estimates of the galactic center pulsar population. Radio surveys of the galactic center have not detected the expected number of pulsars, though this could be because the galactic center environment absorbs and scatters the radio waves pulsars emit in ways that make them hard to see. More sophisticated statistical analyses have looked at whether the gamma ray emission is smooth, as you'd expect from dark matter, which is distributed smoothly, or clumpy, as you'd expect from a population of discrete point sources like pulsars. Different groups have gotten different results. Some analyses find evidence for clumpiness consistent with pulsars. Others find a smooth residual that clumpiness can't fully explain. The debate is ongoing, the signal is real, its origin is uncertain. And then, in 2023, something new was added to the picture. The Fermi Large Area Telescope, after more than 15 years of continuous operation, produced a new analysis of the galactic center region with improved event reconstruction and a better understanding of the diffuse gamma ray emission that serves as the background against which the GCE must be measured. The new analysis confirmed the excess, but it also refined its spatial morphology, the shape of the distribution on the sky. The refined morphology is slightly boxy, not quite perfectly spherical. A perfectly spherical distribution would favor dark matter. A boxy distribution would be more consistent with a stellar population following the boxy bar structure of the inner Milky Way. But here's the thing, the boxiness is subtle, and the dark matter halo of the inner galaxy might itself be somewhat triaxial, not a perfect sphere but an oblate or prolate ellipsoid, in which case dark matter annihilation could also produce a slightly non-spherical signal. So the morphology doesn't definitively rule out dark matter, it doesn't confirm pulsars, it adds more information to a puzzle that keeps accumulating pieces without producing a clear picture. Meanwhile, an entirely separate line of evidence has been quietly building at a different wavelength and from a very different part of the sky. Chapter 6. The X-ray Lines. In 2014, the same year Hooper and Goodenough's dark matter paper was generating discussion, a separate team announced a different anomalous signal. This one was in X-rays, and it came from the Perseus galaxy cluster, from the Andromeda galaxy, and from a composite spectrum of 73 galaxy clusters observed by the XMM Newton Space Telescope. The signal was a spectral line at an energy of approximately 3.55 kilo-electron-volts, a narrow spike in the X-ray spectrum where no known spectral line of any known element should appear. The line was faint, but it was there, and it appeared in multiple, independent observations of multiple different objects. Spectral lines are produced when atoms absorb or emit photons of specific energies, corresponding to transitions between electron energy levels. Every element has its own characteristic set of spectral lines, a fingerprint that allows astronomers to identify the chemical composition of distant objects from their light. A line at 3.55 kilo-electron-volts doesn't match any known atomic transition. The team, led by Ezra Bulbul, proposed an exotic explanation. The 3.55 kilo-electron-volt line could be produced by the decay of sterile neutrinos. Sterile neutrinos are a hypothetical type of neutrino, already a ghostly, nearly undetectable particle that interacts with normal matter only through gravity, and possibly through a very weak mixing with the normal neutrino types. They're a candidate for dark matter, and if they exist with a mass corresponding to the observed line energy, they would occasionally decay, producing a photon, a gamma ray or X-ray, at a specific energy. The 3.55 kilo-electron-volt line is exactly the energy you'd expect from a sterile neutrino dark matter particle with a mass of approximately 7.1 kilo-electron-volts, decaying into a photon and a normal neutrino. This signal has been enormously controversial. It has been detected by multiple groups and multiple telescopes in multiple objects, including, crucially, in a stacked analysis of galaxy clusters and in observations of the galactic center itself. But it has also been challenged by analyses that claim to not detect it, and by arguments that certain known atomic transitions, particularly a sulfur line and chlorine line, could under certain plasma conditions produce emission near 3.55 kilo-electron-volts that has been misidentified. The debate about the 3.55 kilo-electron-volt line is still active, and it has taken on new urgency because of a new telescope. XRISM, the X-ray imaging and spectroscopy mission, launched by JAXA and NASA in 2023, carries a calorimeter instrument called Resolve that can measure X-ray spectra with a spectral resolution roughly 30 times better than XMM Newton. If the 3.55 kilo-electron-volt line is real, XRISM should be able to measure it with enough precision to determine whether it's consistent with a dark matter decay origin or with known atomic transitions. Early results are pending. The astronomical community is watching extremely carefully, because if the line is confirmed as dark matter, if XRISM produces a spectrum of the Perseus cluster or the galactic center with a clean, narrow line at 3.55 kilo-electron-volts that cannot be explained by normal atomic physics, the implications are staggering, not just for dark matter, for our entire understanding of the particle physics that underlies everything. Chapter 6b, the infrared excess and the dust that shouldn't be there. There's a layer of the galactic center mystery that doesn't get discussed in the popular press as often as the gamma ray excess or the orbital anomalies, but which has been quietly accumulating its own set of contradictions for years. It involves dust. Specifically, it involves the fact that there is far more warm dust in the galactic center region than any model predicts, distributed in ways that don't match the expected heating sources, and glowing in the infrared with an intensity that forces uncomfortable questions about where the energy is coming from. Dust in space is not exotic, it's everywhere. Tiny grains of silicates, carbon compounds, and ice that form in the envelopes of aging stars and are distributed through the interstellar medium by stellar winds and supernova explosions. In the galactic center, this dust is extraordinarily dense, which is one of the reasons the region is opaque to visible light. The dust absorbs optical and ultraviolet radiation from stars and re-emits it as infrared radiation. This is a well-understood process. Measure the temperature of the dust grains, and you can calculate how much energy they need to absorb from nearby stars to maintain that temperature. Compare that to the known stellar population, and you can predict how much infrared emission you should see. The galactic center emits more infrared than the stellar population can explain, Not marginally more, significantly more in specific temperature ranges that suggest the excess emission is coming from dust that is warmer than the surrounding stellar radiation field should heat it to. You need an additional heating source, and that additional heating source has to be compact and centrally concentrated, because the excess peaks toward the innermost region of the galactic center and falls off with distance from Sagittarius A star. The obvious candidate for the extra heating is the accretion flow around Sagittarius A star itself, but as we've discussed, Sagittarius A star is extraordinarily underluminous. Its current accretion rate produces too little radiation to account for the excess dust heating, not by a small margin, but by orders of magnitude. Several explanations have been proposed. Perhaps there are unresolved populations of compact stellar remnants, accreting neutron stars or stellar mass black holes, distributed through the galactic center that contribute additional heating without being individually detected. This is plausible but hard to verify, because unresolved sources are, by definition, sources you can't resolve. Population synthesis models suggest that the galactic center should contain tens of thousands of stellar mass black holes in the central parsecs, many of which could be accreting from the surrounding gas. Their combined luminosity might explain some of the infrared excess, but the number of accreting black holes required to explain the full excess is larger than the population models comfortably accommodate. Another possibility involves magnetic reconnection. In regions of very strong disordered magnetic fields, exactly the kind of fields we observe in the galactic center, magnetic reconnection events can rapidly convert magnetic energy into heat. If the galactic center magnetic field is undergoing frequent reconnection events at a rate high enough to maintain the observed dust temperatures, this could explain the excess heating without requiring any specific luminous source. But the rate of reconnection required is very high, and maintaining such a rate over long timescales would require a continuous input of magnetic energy that has to come from somewhere. The infrared excess is also spatially complex. It's not a smooth, symmetric glow centered on Sagittarius A star. It has structure, bright clumps, filamentary extensions, regions of particularly warm dust that don't correspond to any known concentrations of massive stars or compact objects. This spatial structure is difficult to explain with any current model and suggests that the heating is neither smoothly distributed nor simply dominated by one central source. JWST has begun probing this infrared excess with sensitivity and angular resolution that previous observatories couldn't match. Early results are revealing that the structure is even more complex than previously suspected, with small-scale clumps and filaments of warm dust at scales that weren't resolved before, and with temperature distributions that don't follow any simple pattern. The community is still processing these results. Their full implications will take years to work out, but the pattern is the same one that shows up everywhere in galactic center science. Look more carefully, and the picture gets more complicated. Resolve the structure, and the structure doesn't match the predictions. Add more sensitivity, and what you find challenges the model you had before. The dust is trying to tell us something, we're not yet sure what. There's one more dimension to the infrared excess that deserves attention, because it connects to a broader issue with the galactic center energy budget. When you add up all the identified heating sources, massive stars, the accretion flow around Sagittarius A star, whatever contribution comes from compact remnants, and compare the total to what's needed to explain all the observed infrared emission, you get a budget that doesn't balance. The galactic center is emitting more energy in the infrared than the identified sources can produce. This energy has to come from somewhere. Energy conservation is not negotiable. In a system we understood completely, we would be able to account for every watt going in and every watt coming out. In the galactic center, we can't. The accounting has gaps, and in physics, gaps in energy accounting are serious. They've historically been among the most productive leads in science. The unexplained energy deficit in nuclear beta decay led to the prediction of the neutrino. The unexplained energy in the cosmic microwave background led to the detailed understanding of the Big Bang. Energy imbalances are not embarrassments, they're clues. The galactic center's infrared energy imbalance is a clue we haven't solved. Chapter 7. The rotation problem nobody could make go away. Before we go further into what's happening at the galactic center specifically, we need to talk about a problem that has defined cosmology for nearly 50 years. because you can't understand why the galactic center anomalies are so disturbing without understanding the framework within which they're supposed to be explained. And you can't understand that framework without understanding the crisis that created it. In the late 1960s and early 1970s, an astronomer named Vera Rubin was doing something that sounds straightforward. She was measuring how fast stars and gas rotate around the center of galaxies. The physics prediction here seemed obvious. In our solar system, planets closer to the Sun move faster because gravity falls off with distance. The Sun's pull is stronger close in, weaker far out. Mercury zips around in 88 days. Neptune takes 165 years. This relationship between orbital speed and distance is called Keplerian rotation, and it's one of the most well-established results in physics. Rubin expected to see the same thing in galaxies. Stars near the galactic center should move fast. Stars far from the center, in the outer reaches of the galaxy, should move slower because they're far from the mass concentration and experiencing weaker gravity. That's not what she found. What Rubin found, and what has been confirmed in hundreds of galaxies since, is that the rotation curves of spiral galaxies are flat. The stars at the outer edges of galaxies move at roughly the same speed as the stars in the interior. They don't slow down with distance. The orbital speed reaches a plateau and then stays there, out to the very edge of the detectable galaxy and beyond. This is impossible if the only matter in the galaxy is the matter we can see. You can prove this with high school physics. If you know the orbital speed of an object and its distance from the center, you can calculate the total mass enclosed within that orbit. Do this for stars at different distances in a galaxy, and flat rotation curves tell you that the mass enclosed keeps increasing with distance. Even in the outer regions, where there are no visible stars, no visible gas, nothing that shows up in any telescope. Something is out there that we can't see, a vast extended halo of invisible matter surrounding every galaxy. It's what we call dark matter, and the rotation curve evidence for it is about as strong as evidence gets in astronomy. You can argue about the nature of dark matter. You can argue about what particles it's made of. You cannot reasonably argue that there's nothing there. But here's what's interesting for our purposes. If dark matter exists in a vast halo around every galaxy, including our own, then the galactic center should have the highest concentration of it. Dark matter halos are denser toward the center, following that Navarro-Frank-White profile we mentioned earlier. The center of the Milky Way should have a cusp, a region of very high dark matter density, right where Sagittarius A star sits. And high dark matter density means more dark matter particles colliding and annihilating, which means more gamma rays, which means the galactic center gamma ray excess we've already described isn't just consistent with dark matter. It's exactly what you'd predict if dark matter exists in a galactic halo of the type that the rotation curves imply. The different threads keep connecting, the rotation curves implying a dark matter halo, the halo implying a central density concentration, the central density concentration implying annihilation signals, the annihilation signals appearing in the Fermi data as the galactic center excess. Each link in the chain is uncertain. Each alternative explanation for each individual observation exists. But the coherence of the picture, the way the anomalies at the galactic center echo problems that show up across the entire universe, is something that keeps physicists awake. Because if the galactic center excess is dark matter, then we've effectively been sitting 26,000 light years from a dark matter annihilation zone our entire existence as a species. And we're only now, with the most sensitive gamma ray telescope ever built, beginning to detect the signal from it. What else might be happening there that we haven't built the instruments to see yet? Chapter 8. The Magnetic Anomaly. In 2022, a team of astronomers using the SOFIA Airborne Observatory, a Boeing 747 with a telescope in the back, published a paper that added another strange piece to the galactic center puzzle. They had mapped the magnetic field structure of the region surrounding Sagittarius A star, and what they found was unexpected. Magnetic fields in the interstellar medium are not unusual. They're woven through the gas and dust that fills the space between stars, aligned by the motion of ionized gas and the rotation of the galaxy, shaped by stellar winds and supernova explosions. In most parts of the galaxy, the magnetic field is roughly parallel to the galactic plane, horizontal, following the rotation of the Milky Way. At the galactic center, the large-scale magnetic field is perpendicular to the galactic plane. It's vertical, pointing up and down out of the disk. This has been known for decades from radio observations, and it's attributed to the unique conditions in the galactic center region. But the SOFIA observations showed something more specific. In the immediate vicinity of Sagittarius A star, the magnetic field structure is extraordinarily ordered. Not just strong, the magnetic fields at the galactic center are 1,000 times stronger than the average interstellar magnetic field, but organized, coherent, aligned in a way that implies a large-scale, stable magnetic structure centered on the black hole. This matters because magnetic fields at this strength profoundly affect everything in their vicinity. They can channel gas flows, they can prevent gas from falling into the black hole by providing magnetic pressure that resists gravity. They can accelerate charged particles to extreme energies. They can determine the geometry of outflows and jets from the black hole. Sagittarius A star doesn't currently have a visible large-scale jet, another thing that's somewhat unusual for a supermassive black hole. Active galactic nuclei, the bright, powerful black holes in other galaxies, typically produce relativistic jets, narrow beams of plasma moving at close to the speed of light, stretching for thousands or millions of light years. Our galactic center black hole, with its ordered magnetic field and its strong but focused magnetic geometry, shows no obvious large-scale jet. Why not? The magnetic field might be part of the answer. A very strong, ordered magnetic field can collimate outflows, focusing them into narrow jets rather than broad winds. But it can also, under certain conditions, suppress jet formation altogether if the magnetic pressure exceeds a critical threshold. Whether Sagittarius A star's magnetic field is suppressing jet formation, collimating a jet we haven't detected, or doing something else entirely is an open question. The SOFIA result also ties into the Fermi bubbles. The sharp edges of the bubbles, the energy they contain, the way they're oriented perfectly perpendicular to the galactic plane, all of these could be shaped by a large-scale magnetic field structure centered on the galactic center. The magnetic field could be acting as a boundary, confining the high-energy electrons that produce the gamma-ray emission, explaining the sharpness of the bubble edges in a way that pure hydrodynamics struggles to do. But magnetic confinement models of the Fermi bubbles require specific magnetic field geometries that don't quite match the observed structure everywhere. And there's a deeper problem. We don't fully understand how such a strong, ordered magnetic field is generated and maintained at the galactic center in the first place. The mechanisms that create large-scale magnetic fields in astrophysical systems, primarily differential rotation of conducting plasma, the dynamo process, don't obviously explain why the galactic center magnetic field has the particular structure it does. Add this to the list of things we're staring at and not fully understanding. Chapter 9. The radio filaments pan out a little from Sagittarius A star, not as far as the Fermi bubbles but a few hundred light years, and you'll encounter another set of structures that have no clear explanation. The galactic center radio filaments. These are thin, straight, elongated structures visible at radio wavelengths, stretching for tens to hundreds of light years, but with widths of only a fraction of a light year. They're strikingly regular, long, thin, parallel lines, like brushstrokes across the background of the galactic center. They're oriented predominantly perpendicular to the galactic plane, consistent with the large-scale magnetic field structure of the region. The filaments were first discovered in the 1980s, and their physical nature has been debated ever since. They're thought to be synchrotron emission, radiation produced by high-energy electrons spiraling along magnetic field lines. The magnetic field strength within the filaments is inferred to be extraordinarily high, even by galactic center standards. The electron energies are in the range of hundreds of giga-electron volts, energies that require some very efficient particle acceleration mechanism. What's accelerating these electrons? One possibility is the interaction between the magnetized filaments and the surrounding interstellar medium. When a fast-moving cloud of gas slams into a magnetized filament, the interaction can accelerate particles through a process related to Fermi acceleration, essentially particles bouncing back and forth across a shock front and gaining energy with each bounce. But the geometry of this acceleration mechanism has to be just right, and not all filaments show the kinds of interacting clouds that would make this work. Another possibility is that the filaments are connected to the central region and are being powered by energy ultimately derived from Sagittarius A star or from the dense stellar cluster surrounding it. But the filaments extend too far from the center for simple radiation from the central region to explain their emission. In 2022, a new radio survey of the galactic centre conducted with the Meerkat telescope in South Africa dramatically increased the known population of filaments. Before the survey, a few hundred filaments were known. The new data revealed over 1,000 of them. The scale and regularity of the filament population was striking enough that researchers began referring to them as a forest of filaments, a term that captures both their profusion and their strange regimented appearance. The Meerkat survey also revealed something else, a new category of filaments oriented horizontally, parallel to the galactic plane rather than perpendicular to it. These horizontal filaments are shorter and appear to be associated with specific sources: supernova remnants, massive star clusters, possibly the Fermi bubble structure. Their existence suggests that the filament population is more diverse than previously thought, possibly arising from multiple different physical mechanisms. A forest of magnetic structures, some vertical and some horizontal, some stretching for hundreds of light years, emitting synchrotron radiation from electrons with energies that require extraordinary acceleration, and we don't have a clean, unified explanation for any of it. The galactic centre, at every scale and every wavelength, keeps presenting new structures that our models struggle with. Chapter 10. What's actually falling in? There's a process that has been happening at the galactic centre for most of the galaxy's history, and it's central to understanding both what Sagittarius A star is and what it might do in the future. Black holes grow by eating. Matter falls in, releasing energy as it spirals through the accretion disk, and whatever crosses the event horizon is gone forever, added to the black hole's mass. The rate at which matter falls into Sagittarius A star determines how luminous it is, how active it is, and what kind of outflows it produces. Right now, Sagittarius A star is eating very little. The accretion rate is estimated to be something like 10 to the power of -8 solar masses per year, essentially a trickle. At this rate, the black hole is extraordinarily quiet. Its luminosity is something like 10 to the power of 33 watts, which sounds impressive until you compare it to what it could be. An actively accreting supermassive black hole at the Eddington limit, converting mass to energy with maximum efficiency, would be many orders of magnitude more luminous. Sagittarius A star is, by these standards, essentially inactive. But essentially inactive doesn't mean completely quiet, and the galactic centre is not a static place. Every day, material from the environment is flowing towards Sagittarius A star. Gas from the stellar winds of the massive stars in the central cluster, dust from disrupted clouds, occasionally the remnants of objects that have passed too close and been tidally disrupted. Most of this material doesn't make it into the black hole directly. It loses angular momentum through various processes and spirals inward gradually. Some of it may be carried away in outflows before it ever crosses the event horizon. What we can observe is the X-ray and infrared emission from the immediate accretion zone, the region within a few hundred Schwarzschild radii of the black hole, and this region is persistently variable. It flares. Sagittarius A star produces X-ray flares roughly once or twice per day. These flares last from minutes to a few hours, and involve the X-ray luminosity increasing by factors of 10 to 100 above the quiescent level. The origin of the flares is not fully understood. They might arise from magnetic reconnection events near the event horizon, similar in some ways to solar flares, or from the temporary formation and disruption of hot, compact plasma structures in the accretion flow. In the near-infrared, the flaring is even more dramatic and more frequent. Sagittarius A star varies in infrared brightness essentially continuously, with large flares occurring multiple times per day. The gravity instrument has been able to resolve the motion of the flaring emission. During bright flares, they observe emission regions that appear to orbit the black hole at roughly the innermost stable circular orbit, the closest that matter can stably orbit before being pulled inward, moving at a significant fraction of the speed of light. This is direct observation of matter moving in the extreme gravity environment right next to a supermassive black hole. It's one of the most extraordinary pieces of observational physics ever achieved. And the measurements show something interesting. The orbital motion of the flaring plasma is roughly consistent with general relativity, but the details of the polarization of the light, which tells you about the magnetic field geometry, are complex and point to a highly dynamical, chaotic environment close to the event horizon. The picture that emerges is of a black hole that is not quietly sleeping, but rather constantly simmering, flaring, varying, occasionally consuming blobs of infalling matter, but doing all of this at a tiny fraction of its theoretical maximum capacity. Why is it so underluminous? Why is it eating so slowly? The galactic center environment has plenty of gas. The mass of gas within a few light years of Sagittarius A star is estimated to be hundreds of times the mass of our Sun. At the inferred accretion rate, it would take tens of billions of years to accrete that mass, far longer than the age of the universe. Something is preventing the gas from falling in efficiently. The magnetic field may be part of the answer, providing magnetic pressure that counters gravity. Thermal pressure from the hot gas in the galactic center environment can also resist infell. Whatever the reason, Sagittarius A star is surrounded by plenty of food. It is largely not eating, unless something changes. Chapter 11. The Echo of a Giant Explosion. We said earlier that Sagittarius A star might have been much more active in the recent past. Recent in astronomical terms means within the last few million years, a blink of geological time. Buteers, a blink of geological time, but also the period within which various traces of that activity might still be detectable. There's evidence that Sagittarius A star has, at least episodically, eaten much more voraciously than it does today. The most striking is what's called the SGRA starlight echo. Light travels at a finite speed. When a flash of light occurs, it takes time for that light to reach other objects and reflect off them. If a very bright flash of X-rays or gamma rays was produced at the galactic center a few hundred years ago, we could detect that flash today not directly. The direct flash would have passed us long ago, but by its reflection off molecular clouds near the galactic center. The light would have traveled from Sagittarius A star to the cloud, reflected off the cloud, and then traveled to us, and depending on the geometry, this reflected light would arrive at different times for different clouds. Astronomers have detected exactly this: molecular clouds near the galactic center glowing in X-rays in patterns consistent with a reflected light echo. The brightening and fading of different clouds follow the geometric pattern you'd expect if they were reflecting a flash from Sagittarius A star that occurred somewhere between 100 and 400 years ago. The inferred luminosity of this flash is startling. Whatever happened at Sagittarius A star around 100 to 400 years ago, based on the brightness of the reflected X-rays, was about 1 million times more luminous than the current quiescent state. That's still far below Eddington limit activity, but it's a dramatic departure from today's near-total quiescence. Something caused Sagittarius A star to flare very brightly just a few hundred years ago, well within recorded human history. What triggered it? The timing corresponds to nothing obvious in the galactic center environment. There's no known major accretion event, no tidal disruption of a star, no large cloud infall, that would explain a flare of this magnitude at that time. And 400 years is recent enough that you have to think about it differently than you think about the Fermi bubbles, which were produced millions of years ago. This flash happened while Galileo was building his first telescopes, while Shakespeare was writing, while the pilgrims were preparing for their voyage to the New World. The galactic center was briefly 1 million times brighter than it is today, and nobody on Earth had any idea, because the galactic center is hidden behind dust clouds so thick that optical telescopes can't see it. But we can see it in X-rays via the reflection, and what we see is a record of a universe that is not static, not predictable, not settled. The galactic center can and does wake up, at least briefly, and the conditions that trigger these awakenings are not understood. The molecular cloud reflection technique has also been used to try to map the history of Sagittarius A star's activity over longer timescales, hundreds to thousands of years. The picture that emerges is of an erratic source, mostly very quiet, occasionally flaring briefly to much higher luminosities, with a pattern of activity not following any obvious regular cycle. It's as if the black hole at the center of our galaxy is not simply a gravitational drain, passively accumulating whatever matter happens to fall in, but an active participant in the environment around it, one that can be triggered by events we don't fully understand, that can briefly brighten by factors of millions, and that has shaped the structure of the galaxy around it through these episodic outbursts over billions of years. The Fermi bubbles might be the biggest trace of a past outburst, the X-ray light echo might be the most recent, and the question that naturally follows is, when is the next one? Chapter 12. The Clocks at the Center. Here's something that sounds like science fiction but is simply physics. Near Sagittarius, a star, time runs differently than it does here. This is not a metaphor. It's a direct consequence of general relativity, which tells us that gravity dilates time. The stronger the gravitational field, the slower time passes relative to a distant observer. Near a black hole, this effect becomes extreme. For the stars orbiting Sagittarius, a star at distances of a few light hours, the S-stars at their closest approaches, the gravitational time dilation is measurable. A clock on the surface of a star at S2's periapsis distance would tick measurably slower than a clock far from the galaxy. Not dramatically slower, S2 is not close enough for extreme relativistic effects, but measurably slower. The gravity team has actually detected this effect as a gravitational redshift in the light from S2 during its close approach. The light is shifted to longer wavelengths, consistent with it climbing out of a gravitational well, but closer in, much closer, within a few times the Schwarzschild radius of the black hole, time dilation becomes extreme. At the event horizon itself, from the perspective of a distant observer, time stops entirely. Matter crossing the event horizon appears to freeze, its image dimming exponentially as the light it emits becomes infinitely redshifted. Inside the event horizon, if you could survive the tidal forces and get there, general relativity predicts that time and space essentially swap roles. The future becomes a direction in space rather than in time. You cannot avoid hitting the singularity at the center any more than you can avoid the future from where you sit right now. Except that this prediction, the singularity, is where general relativity breaks down. The theory predicts a point of infinite density, infinite curvature, infinite everything, and infinite is physics' way of saying, this theory doesn't work here anymore. Something else must happen at the singularity, some physics we don't yet have, some theory that merges general relativity with quantum mechanics, must take over. We don't have that theory, we have candidates, string theory, loop quantum gravity, various other approaches. None of them are confirmed, none of them make predictions that are testable with current technology. We are, in a very real sense, at the edge of what we know. At the galactic center, 26,000 light-years away, there is a place, inside the event horizon of Sagittarius, a star, where our best theory of gravity predicts something that cannot be right, and our best alternative theories can't tell us what is actually happening. The singularity is not just a mathematical curiosity, it represents a fundamental incompleteness in our understanding of nature, and it sits at the center of our galaxy. Some physicists have proposed that the singularity doesn't exist, that quantum effects near the center of a black hole prevent the formation of an infinitely dense point. In some models, the collapsing matter reaches a quantum mechanical limit and bounces, creating an expanding core that pushes outward against the infell. Some models predict that black holes might eventually transition into something different, a white hole that expels matter rather than consuming it, or a Planck star in which quantum gravity creates a new kind of ultra-dense equilibrium state. These ideas are speculative, they're mathematically motivated but observationally unconfirmed. The interior of a black hole is by definition causally disconnected from us. Nothing that happens there can send us a signal, because no signal can escape the event horizon. We cannot directly observe what's inside Sagittarius, a star, but we can observe the event horizon and its immediate vicinity, and the EHT observations of the black hole shadow, the gravity observations of the orbital dynamics of accreting plasma, and the future observations planned with even more sensitive instruments will continue to push the limits of what we can test. If quantum gravity effects near the event horizon are large enough to be detectable, which most theories predict they aren't, but some unusual models suggest they might be, those observations might one day catch a hint of physics beyond general relativity without requiring a trip inside the event horizon. Chapter 12. B. The cosmic ray excess and the accelerator. We can't find every second. The Earth is bombarded by cosmic rays, high-energy charged particles, mostly protons and atomic nuclei, that travel through the galaxy at nearly the speed of light and rain down on us from all directions. Most of them are stopped by the atmosphere. The few that make it through create brief showers of secondary particles that are detectable by experiments on the ground. The most energetic cosmic rays carry energies that dwarf anything achievable by any particle accelerator humanity has built or is likely to build. Where do cosmic rays come from? The most energetic ones remain mysterious. But for cosmic rays in the energy range that dominates the galactic flux, energies below what's called the knee in the cosmic ray spectrum, around a few petaelectron volts. The leading explanation is supernova remnants. When a massive star explodes as a supernova, the expanding shock wave acts as a natural particle accelerator, bouncing charged particles back and forth across the shock front and ramping them up to enormous energies through a process called diffusive shock acceleration. This mechanism is theoretically well understood and observationally supported by the detection of gamma rays from supernova remnants. Gamma rays that are produced when the accelerated cosmic rays collide with interstellar gas. The galactic center should be a particularly rich environment for cosmic ray production. The dense stellar population means frequent supernovae. The strong magnetic fields and high gas density create ideal conditions for acceleration and confinement. And indeed, the galactic center region is one of the brightest sources of high-energy gamma rays in the sky, which is exactly what you'd expect if it's producing and confining large quantities of high-energy cosmic rays. But the distribution and spectrum of cosmic rays in the galactic center region doesn't match what supernova remnants alone can explain. In 2016, the HESS collaboration, an array of Cherenkov telescopes in Namibia, published an analysis of the very high-energy gamma ray emission from the galactic center region. They found that the emission had a spectral shape and spatial distribution consistent with a population of cosmic ray protons with energies extending up to a few petaelectron volts. Exactly the knee energy that has been puzzling cosmic ray physicists for decades. The spatial distribution of the emission traced the distribution of interstellar gas in the galactic center region, exactly as expected if cosmic rays were being produced centrally and then diffusing outward through the gas. But the source of those PeV-energy cosmic rays wasn't obvious. The known supernova remnants in the galactic center region can't quite produce particles at these energies efficiently enough. The spectrum and total power require a source of extraordinary efficiency, something the HESS team called a PeVatron, a cosmic ray accelerator capable of reaching PeV energies, and the data pointed to the source being near or at Sagittarius A star itself. Sagittarius A star is a PeVatron. The idea is not absurd. Black hole environments can, in principle, accelerate particles to very high energies through various mechanisms involving the strong magnetic fields and the electromagnetic fields generated by the spinning black hole. If Sagittarius A star is spinning, which is itself an open question, its spin parameter hasn't been precisely measured. But the details of how a currently quiescent black hole like Sagittarius A star produces a continuous stream of PeV-energy cosmic rays are not understood. One model invokes the strong magnetic field in the immediate accretion zone, which can accelerate particles through a process called magnetic centrifugal acceleration near the black hole's ergosphere, the region just outside the event horizon where the black hole's rotation forces everything to co-rotate. This mechanism is theoretically capable of reaching PeV energies for the mass and spin of Sagittarius A star, but requires specific geometric conditions that may or may not be present. Another model suggests that the PeVatron activity is not currently associated with Sagittarius A star, but is a relic of the past active period that produced the Fermi bubbles. Cosmic rays accelerated during the peak of Sagittarius. A star's past activity could still be present in the galactic center region, their energy gradually being lost through collisions with gas and radiation, producing the gamma ray signal we observe today. This model predicts that the cosmic ray spectrum should have a specific shape, reflecting the aging of the particle population, and the observed spectrum is broadly consistent with this prediction, but not definitively. The HESS detection was followed up by the MAGIC and Veritas arrays, and more recently, by the LHASSO experiment in China, a ground-based extensive air shower array with unprecedented sensitivity at the highest energies. LHASSO has detected multiple PeVatrons across the galaxy and has refined the galactic center measurements. The results confirm that something at or near the galactic center is accelerating particles to PeV energies. The identity of the accelerator remains contested. This matters beyond the purely academic. Cosmic rays are not passive observers of the galactic center environment. They interact with the gas, heating it, ionizing it, driving turbulence that affects everything from star formation rates to the stability of molecular clouds. The cosmic ray pressure in the galactic center region is a significant component of the overall pressure balance that determines how gas moves and accumulates. If the cosmic ray source is time variable, if it was more powerful in the past, when Sagittarius A star was more active, then the history of cosmic ray production at the galactic center is intertwined with the history of everything else: the Fermi bubbles, the star formation history, the distribution of molecular gas, the formation of the G objects. Everything in the galactic center connects to everything else. Pull on any thread and the whole fabric shifts. And the more we learn about the cosmic ray environment at the galactic center, the more threads appear that we haven't pulled yet. Chapter 13. The Tidal Disruption. Events. Not far from our galaxy, in the distant universe, telescopes regularly catch the spectacular death throes of stars that wander too close to supermassive black holes. These events are called tidal disruption events, TDS, and they're among the most energetic transient phenomena in the universe. A star following an innocent enough trajectory through the galaxy comes too close to the central black hole, passes within the tidal radius, where the black hole's gravity overwhelms the star's own self-gravity and is ripped apart. Half the stellar debris escapes. The other half falls back onto the black hole, forming a temporary accretion disk that blazes with extraordinary luminosity for months or years before fading. TDS are detected in distant galaxies several times per year now, and they've given us a window into black hole feeding in action. The rate at which they occur in any given galaxy depends on the density of stars near the central black hole. The more densely packed the stellar population, the more frequently stars scatter off each other into unfortunate orbits that carry them close to the black hole. The galactic center of the Milky Way, with its extraordinarily dense stellar population, tens of millions of stars per cubic parsec in the central regions, should have one of the highest TDE rates of any galaxy we know. Estimates suggest that a star should be tidally disrupted by Sagittarius A star roughly every 10,000 to 100,000 years. We haven't directly observed a TDE from Sagittarius A star. This isn't surprising. 10,000 years is a long time, and we've only been watching the galactic center carefully for a few decades. But the X-ray light echo evidence we discussed earlier might be related to a TDE or a partial TDE that occurred a few hundred years ago. A partial tidal disruption, where a star passes close enough to have its outer layers stripped but survives as a remnant, would produce a flare of lower luminosity and shorter duration than a full TDE, which is consistent with what the light echo data suggests. The G objects we discussed in Chapter 3 might also be related to this story. One hypothesis for the origin of these gas-enshrouded objects is that they're the results of stellar encounters near the black hole, close passages that stripped the outer layers of one or more stars, creating gas and dust-wrapped remnants that continue on their modified orbits. If this is correct, the G objects are, in a sense, the survivors of events that weren't quite destructive enough to be full TDEs. But there's a more dramatic possibility lurking in the data. Astronomers have noticed that the rate of X-ray flares from Sagittarius A star has varied significantly over the period we've been monitoring it. In 2019, the galactic center suddenly became dramatically more active in the near-infrared, the brightest flare observed in the 2 decades of monitoring the source, for reasons that remain unclear. The flare was about twice as bright as any previously recorded, which is startling for a source that normally varies by factors of tens to hundreds. The timing of this unusual activity is interesting. It occurred a year after the G2 cloud made its close approach to Sagittarius A star, which had itself failed to trigger the expected increase in accretion activity. But perhaps G2 deposited material that took a year to circulate and begin accreting? Or perhaps the 2019 flare is unrelated to G2 and represents the beginning of a new epoch of slightly elevated activity for reasons connected to something else in the galactic center environment. The data since 2019 suggests that Sagittarius A star may indeed be somewhat more variable than it was in the preceding decade. The baseline of activity seems to have shifted upward slightly, not dramatically, not toward anything approaching active galactic nucleus levels, but enough to notice. If the black hole is entering a slightly more active phase, even temporarily, the implications for the surrounding environment are significant. Even a modest increase in Sagittarius A star's accretion rate would increase the radiation environment in the galactic center, potentially affecting the structure of gas clouds, the formation of molecules, and the acceleration of cosmic rays in the region. And if the increased activity is the beginning of a longer-term trend, if Sagittarius A star is, in geological timescales, stirring, the galactic center environment could look significantly different in 1 million years than it does today. There is even more speculative territory here. Some researchers have noted that the Milky Way is currently in the early stages of merging with the Magellanic Clouds, smaller satellite galaxies that are falling into the Milky Way under gravity. This interaction is disturbing the distribution of stars and gas in the outer galaxy. On much longer timescales, billions of years, the Milky Way will also merge with the Andromeda Galaxy. These mergers will eventually drive enormous amounts of gas toward the galactic center, potentially reawakening Sagittarius, a star, to something approaching quasar-level activity. The galactic center is not static. The black hole at its heart is not permanently sleeping, and the eventual waking of that sleeping giant, whenever it occurs, will reshape the inner galaxy in ways that are difficult to model and impossible to fully predict with current understanding. Chapter 14. The problem with our models. Let's step back from the specific observations and talk about something more fundamental. Because the individual anomalies, the orbital puzzles, the G-objects, the galactic center excess, the X-ray lines, the Fermi bubbles, the radio filaments, are disturbing in their own right. But the deeper issue is what they collectively reveal about the state of our theoretical understanding. Our models of the galactic center, the simulations and analytical frameworks we use to predict how gas flows, how stars orbit, how the black hole feeds, how energy propagates through the region, are built on several foundational assumptions. General relativity governs gravity. Magnetohydrodynamics governs the behavior of ionized gas in magnetic fields. Stellar evolution determines how stars are born, live, and die. The large-scale structure of dark matter halos is determined by cosmological simulations. These are not bad assumptions. They're based on physics that works extraordinarily well in the environments we've tested it in. The galactic center is not like the environments we've tested it in. The stellar density is millions of times higher than the galactic average. The magnetic fields are thousands of times stronger. The gravitational field includes not just the 4 million solar mass black hole, but a dense stellar mass black hole population, neutron stars, and possibly a dark matter cusp that we can't directly observe. The radiation environment is extreme. Tidal forces shear clouds before they can collapse. The velocities of gas flows are enormous. The timescales on which everything changes are shorter than anywhere else in the galaxy. When you run simulations of the galactic center, you have to make choices about what physics to include and at what resolution to model it. Including all the relevant physics at the resolution needed to capture the small-scale structures we observe would require computers orders of magnitude more powerful than anything currently in existence. So you simplify, you approximate, you hope that the approximations don't qualitatively change the answers, and then the observations come back and the answers are wrong. Not every prediction fails. Many aspects of the galactic center are well described by current models. The overall dynamics of the stellar cluster, the broad features of the gas distribution, the spectrum of synchrotron emission from the central region, these are reasonably well reproduced. But in the places where the models and observations most strongly diverge, the paradox of youth, the G-object survival, the persistence of the galactic center, gamma-ray excess, the structure of the radio filaments, the divergences point not to minor errors in parameter choices, but to possible gaps in our fundamental understanding. Consider the paradox of youth one more time. The stars near Sagittarius are a star that shouldn't exist. Too young to have migrated from afar, too close to have formed in situ according to standard star formation physics. One class of proposed solutions invokes disk-driven migration, in which stars form in an episodic accretion disk and then migrate inward through gravitational torques as the disk dissipates. This works mathematically under some assumptions, but the current best simulations of this process produce stellar distributions that don't quite match what's observed. The orbital inclinations are wrong, the eccentricities are wrong, the ratio of clockwise orbiting to counterclockwise orbiting stars doesn't match. Small discrepancies perhaps, but discrepancies that resist being eliminated no matter how the models are tuned. Physics has a name for this situation, though it doesn't use it officially. The models are overfit to the data they were designed to explain and underpredicting the data they weren't. That's not a judgment on the scientists who build the models. It's a structural feature of complex systems that reveals itself when you look at them from a new angle, or at a new precision, or in a new wavelength. The galactic center keeps being looked at from new angles, and the new views keep revealing new misfits. Some researchers believe the misfits are symptoms of missing physics, processes that are known in principle but haven't been properly incorporated. Better treatment of stellar feedback, more realistic magnetic field evolution, improved models of how binaries interact in dense stellar environments. Others believe the misfits are pointing to something more fundamental, to physics beyond our current standard models, to the presence of matter or energy that we haven't identified, to dynamics near the event horizon that general relativity doesn't capture because general relativity is incomplete. The divide between these camps is not absolute. Most scientists would say, probably some missing physics, possibly something more fundamental, and let's keep looking. But the possibly something more fundamental camp has been growing as the anomalies accumulate and the attempts to explain them with conventional physics repeatedly fall just short. Chapter 15. New Eyes Opening. The situation is not static. The instruments we're bringing to bear on the galactic centre are becoming dramatically more powerful, and the next decade is likely to produce more data about the galactic centre than the entire history of observation before it. The Event Horizon Telescope has continued operating since the 2022 image of Sagittarius A star, and plans are underway to expand the array with new stations in Africa, Asia, and potentially Antarctica that will significantly improve its resolution and sensitivity. The next generation EHT-NGEHT aims to produce not just static images of the black hole shadow, but actual movies, time-resolved reconstructions of how the accretion flow changes on the timescales of the orbital period near the event horizon, which for the innermost stable circular orbit around Sagittarius A star is only about 30 minutes. These movies will directly test our models of accretion physics in the strongest gravitational environments we can observe. The gravity instrument at the Very Large Telescope Interferometer in Chile, which has already produced extraordinary results on the S-star orbits and the flaring emission, is being upgraded to Gravity Plus, which will improve its sensitivity by a factor of several and extend its reach to fainter sources. With Gravity Plus, astronomers plan to track fainter stars in orbits even closer to Sagittarius A star, providing even more precise tests of general relativity in the strong field regime, and potentially detecting the effects of the extended dark mass that might explain the orbital residuals. The Square Kilometre Array, SKA, currently under construction in South Africa and Australia, will be transformative for radio observations of the galactic centre. Its sensitivity will be orders of magnitude beyond current radio telescopes, and it will be able to detect pulsars near Sagittarius A star, if any exist with favourable timing properties. A pulsar orbiting the black hole would be one of the most extraordinary laboratories in physics, a natural clock in a strong gravitational field, whose timing provides direct measurements of the spacetime geometry near Sagittarius A star. Finding even one such pulsar would allow tests of general relativity and quantum gravity at precisions that no human-built experiment could approach. The SKA will also dramatically improve our understanding of the radio filament population and the large-scale magnetic field structure of the galactic centre. With sufficient sensitivity and angular resolution, it may be possible to track the motion of ionized gas within individual filaments, directly measuring the flow velocities and magnetic field strengths, rather than inferring them from integrated emission. In gamma rays, the next generation of ground-based Cherenkov telescope arrays, particularly the Cherenkov Telescope Array Observatory, CTAO, also currently under construction, will provide significantly improved sensitivity and angular resolution for high-energy gamma rays from the galactic centre. The CTAO will be able to much more precisely map the spectrum and morphology of the galactic centre gamma ray excess, providing much better discrimination between the dark matter, annihilation hypothesis, and astrophysical explanations like millisecond pulsars. In X-rays, XRISM, already launched, and the future Athena mission, a large European X-ray observatory, will provide high-resolution spectroscopy of the galactic centre region. If the 3.55 kilo-electron-volt line is dark matter, Athena will characterise it with enough precision to essentially prove the case. If it's atomic transitions, Athena will show that too. In the infrared, the James Webb Space Telescope, JWST, is already observing the galactic centre at sensitivities and angular resolutions that previous infrared telescopes couldn't approach. JWST has begun revealing the galactic centre stellar population in unprecedented detail, finding stars that were too faint to detect before, characterizing the properties of the G-objects with higher precision and probing the dust structure that makes the galactic center visible in infrared but hidden in optical light. Early JWST results from the galactic center have already turned up surprises. The stellar population in the inner parsec shows features that weren't expected. Populations of stars with properties that don't fit neatly into the standard models of galactic center stellar evolution. These results are preliminary, and their interpretation will take time. But the pattern is consistent with what every new high-sensitivity observation of the galactic center has shown. Things are not quite as the models predicted. The next decade will bring a torrent of new data. The galactic center will be observed with more eyes, at more wavelengths, at higher precision than ever before. And that means the anomalies will either be resolved, explained by new and better models, or they will deepen. Based on the history of galactic center science, the smart money is on deepening. Chapter 16. What the scientists are actually saying. We've covered a lot of ground. Let's get specific about the scientific discourse, because there's a real difference between what's actually being said in the research literature and what the headline-grabbing framing might suggest. No mainstream astronomer is publicly claiming that the galactic center proves the existence of dark matter. No mainstream physicist is publicly claiming that the 3.55 kilo electron volt line definitively requires sterile neutrino decay. No theorist in good standing is seriously proposing that general relativity has failed at the galactic center in some dramatic way. What's actually happening is more subtle, and in its subtlety more interesting. There is a growing sense in the community that the galactic center is a region where the standard paradigm is under stress. Not broken, stressed. The models explain many things but fail in specific ways. The data is consistent with conventional physics, but consistently shows residuals that resist conventional explanation. The alternative explanations, dark matter, exotic particles, new gravitational physics, are not required by any single observation, but each alternative explanation continues to remain viable when it should, by now, have been ruled out. That persistence is what makes scientists uneasy. In science, when you have an anomaly, the expectation is that as data improves, the anomaly either goes away, it was a statistical fluke, a systematic error, a misunderstood astrophysical process, or it sharpens into something definitive. We now know it's real, and it requires new physics. The galactic center anomalies have been doing neither. They persist. They don't sharpen into clear signatures. They don't disappear into better understood backgrounds. They sit in a frustrating middle ground, too significant to ignore, too ambiguous to definitively interpret. The galactic center gamma ray excess has been studied for over a decade with increasing sophistication. Papers continue to appear arguing for pulsars. Papers continue to appear arguing for dark matter. The debate is not resolved. The 3.55 kilo electron volt line has been detected and challenged repeatedly. The next telescope, XR-ISM, should be able to resolve it. We're waiting. The orbital anomalies of the S-stars have been measured to higher and higher precision. The residuals persist but don't grow in a way that clearly demands a specific new component. They might be dark matter. They might be a population of stellar mass black holes. They might be a measurement systematic that hasn't been identified yet. What the scientists are actually saying in the honest spaces of their papers and conference talks is something like, we have multiple independent observations of the galactic center region that are not fully explained by any single consistent model using only known physics. The dark matter hypothesis, particularly WIMP annihilation and sterile neutrino decay, provides a consistent framework that would simultaneously explain several of these observations. We haven't ruled it out. We haven't confirmed it. We need more data. That's the careful, calibrated truth. But there's another truth running alongside it, in conversations after the formal talks are over, in the comment sections of preprints, in the late-night exchanges at conferences. It's the recognition that we've been saying we need more data about the galactic center anomalies for a long time, that the expected resolutions haven't materialized, that the parameter space for conventional explanations has been squeezed from multiple directions simultaneously, and what's left is smaller than it used to be. Some of the most cautious, most rigorous scientists in the field, people who have spent entire careers insisting on conservative interpretations, are starting to say that the pattern of anomalies is beginning to look like it might be telling us something fundamental. not any single observation, the pattern. Patterns are hard to quantify. You can't put a p-value on a feeling that something is off, but science has always operated on both the formal and the informal. The peer-reviewed result and the intuition of experienced observers who have spent decades understanding how data from a complex system is supposed to look. And a growing number of those experienced observers are saying, this doesn't look right. Chapter 16b. The possibility nobody wants to name. There is a hypothesis about the galactic center that circulates in the more speculative corners of the theoretical physics community, that gets mentioned in footnotes and in informal discussions, and that almost nobody puts at the center of a paper because doing so invites the kind of skepticism that can define a career in the wrong way. It's not a fringe idea exactly. It has mathematical motivation and some observational support. But it's uncomfortable enough that it tends to be approached sideways, mentioned as a possibility to be tested rather than a conclusion to be drawn. The hypothesis is this. The anomalies at the galactic center are not independent puzzles with individual conventional solutions. They are symptoms of a single underlying phenomenon that conventional physics has no framework for. And that phenomenon might be something in the category of what theorists call new dark sector physics. Not just dark matter particles that annihilate occasionally, but a rich, complex dark sector with its own forces, its own dynamics, and its own structures that are gravitationally coupled to the visible universe, but otherwise completely hidden from us. The standard picture of dark matter is simple. Particles. They have mass. They feel gravity. They occasionally annihilate. End of story. But this simple picture has been under pressure for years. Underground detectors searching for direct dark matter interactions have not found the signals expected from the simplest WIMP models. The Large Hadron Collider, which operates at energies where WIMPs should have been produced if they exist with the predicted masses, has found nothing beyond the standard model. The simplest dark matter models are running out of parameter space. What if dark matter is not simple? What if the dark sector, whatever collection of particles and fields makes up the non-luminous 27% of the universe, has internal structure? What if there are dark matter particles that interact not just gravitationally, but through some dark force that is completely invisible to standard model physics? What if there are dark atoms, dark chemistry, dark stars, dark compact objects, an entire shadow universe of complexity that is gravitationally intertwined with ours, but otherwise wholly separate? This is called self-interacting dark matter in its milder forms, and complex dark sector, or dark matter with dark forces, in its more elaborate variations. The idea has been gaining traction because self-interacting dark matter solves several problems with a simple cold dark matter picture. It better reproduces the observed distribution of dark matter in galactic halos, it better explains the properties of small satellite galaxies, and it reduces some discrepancies between cosmological simulations and observations. In the galactic's center specifically, self-interacting dark matter predicts a different density profile than the standard NFW profile. Instead of an infinitely rising cusp at the center, self-interacting dark matter forms a core, a region of approximately constant density within some radius. This changes the predicted signal from dark matter annihilation in ways that affect the interpretation of the galactic center excess. Some analyses find that the spatial morphology of the excess is better fit by a chord profile than by the standard NFW cusp, which would be consistent with self-interaction. Others find the opposite. The data quality hasn't been sufficient to definitively discriminate. But here's where it gets interesting. If dark matter self-interacts strongly enough to form cores in galactic halos, it might also be capable of forming much more compact structures, dark matter analogues of stars or clusters, held together by dark sector forces rather than standard model physics. These dark, compact objects would be gravitationally detectable, but otherwise invisible. They would perturb the orbits of stars and gas in the galactic center without producing any electromagnetic signal. They might explain the extended mass component hinted at in the S-star orbital residuals without being made up of stellar remnants or ordinary matter. Could there be dark, compact objects in the galactic center of the Milky Way, orbiting Sagittarius A star in a kind of dark matter cluster that we can't see but can feel? Could some of the anomalous orbital properties of the S-stars be caused by gravitational perturbations from structures that are literally invisible to every telescope we have? Could the energy imbalance in the galactic center's infrared emission be connected to heating by a dark sector process? Dark matter annihilation within a dense dark core producing standard model particles that thermalize and heat the surrounding dust? These questions are speculative. The answers might all be no. But the fact that they can't be definitively ruled out, that the observational constraints on such scenarios are not yet tight enough to exclude them, is itself a measure of how incomplete our understanding of the galactic center is. We cannot rule out an invisible dark matter cluster at the center of our galaxy. We don't have the tools yet to either confirm it or definitively eliminate it. The next generation of instruments, particularly Gravity Plus and the SKA, will tighten the constraints significantly. Precise measurements of the S-star orbits will either sharpen the evidence for an extended mass component or show that the residuals are consistent with zero. Pulsar timing near Sagittarius A-star will probe the gravitational field in the galactic center with extraordinary sensitivity, potentially detecting or ruling out dark compact objects with masses as small as 1,000 solar masses. Until those measurements exist, the most honest statement about the galactic center is that we don't know what's there. Not just in the sense of not having solved an equation, in the sense of not knowing the inventory, not being certain we've identified all the significant contributors to the mass, the energy, the dynamics of the region. At the center of our galaxy, the most observed patch of extreme astrophysics in the universe, there might be things we haven't imagined yet. Not because we lack imagination, because the universe's imagination appears to exceed ours. That's not a comfortable position for science to be in. It's also exactly the position science should be in when it's doing its job correctly, not satisfied with the current map, always aware that the territory is larger than what's been charted, always suspecting that the next observation will show something the last model didn't predict. The galactic center has been doing this to us for 50 years. It will keep doing it. And the scientists who study it, the ones who live with the anomalies, who have sat with the data long enough to feel its texture, who know where the models creak and where they break, are both the most excited and the most uneasy people in astronomy. They're excited because they're at the frontier. They're uneasy because they can't see over it yet. And somewhere beyond that frontier, in the warm glow of 4 million solar masses of compacted spacetime, the answers are waiting. Chapter 17. What it would mean. Let's ask the question that this entire investigation has been building toward. If the galactic center anomalies are pointing to something real, to physics beyond the standard model, to dark matter signals, to new gravitational physics, what would that actually mean? If the galactic center gamma-ray excess is confirmed as dark matter annihilation, it would be the first direct detection of dark matter particles in history. Not indirect evidence, not the galaxies rotate in a way consistent with dark matter being there, but actual signal produced by actual dark matter particles colliding and converting to standard model particles we can detect. It would confirm the WIMP hypothesis that has been the leading dark matter candidate for decades. It would tell us the mass of the dark matter particle, constrain its interaction cross-section, and give us a target for direct detection experiments. The underground detectors filled with liquid xenon or germanium crystals, waiting to feel the faint recoil of a dark matter particle passing through the Earth. The implications would cascade across physics. We would know the identity of 85% of the matter in the universe. We would have a handle on the particle physics of the dark sector. The standard model would need to be extended to include the new particle. The theoretical framework would need to accommodate whatever symmetry or mechanism produces a particle with exactly the properties the dark matter particle has. It would, without exaggeration, be the most significant discovery in physics since quantum mechanics. If the 3.55 kilo-electron-volt line is confirmed as sterile neutrino decay, the implications would be equally profound and somewhat different. Sterile neutrinos are predicted by extensions of the standard model that address several problems simultaneously, not just dark matter but also the origin of neutrino masses, and possibly the matter-antimatter asymmetry of the universe. A sterile neutrino detection would not just solve dark matter, it might explain why the universe contains matter at all, rather than being a sterile mixture of matter and antimatter that would have annihilated at the beginning. If the orbital anomalies of the S-stars turn out to require new gravitational physics, some modification of general relativity that becomes apparent only in the specific regime near a supermassive black hole, the implications would be harder to predict because they would depend on what the modification is. various modified gravity theories exist that make predictions different from general relativity in specific regimes. Most of them have been ruled out by other observations, but the galactic center, with its unique combination of extreme gravitational potential and high matter density, might provide a test that discriminates between general relativity and some of its competitors in a way that other observations can't. A failure of general relativity at the galactic center would not, in all likelihood, mean that general relativity is simply wrong. It would more likely mean that general relativity is an approximation to a deeper theory, just as Newtonian gravity is an approximation to general relativity. The deeper theory would need to agree with general relativity everywhere, that general relativity agrees with observation, which is essentially everywhere except the singularity and possibly the galactic center. This kind of scientific revolution, a deeper theory that subsumes and extends a successful existing theory, is the most common type of paradigm shift in physics. It doesn't erase what came before, it places it in a broader context and reveals where the boundaries are. The galactic center, with its unique combination of extreme conditions, might be one of the places where we first see over the edge of those boundaries. Chapter 18: The Quiet Panic. The title of this video uses a phrase, quietly panicking, that deserves some examination, because scientists don't usually panic. The culture of science is deliberately calm, deliberately measured, trained from graduate school onward to resist the impulse to draw dramatic conclusions from ambiguous data. But there's a type of scientific discomfort that doesn't announce itself. It accumulates in the revision history of papers, in the footnotes of grant proposals, in the careful hedging of conclusions that used to be stated more confidently. It shows up when a researcher who has spent 20 years building models of galactic center gas dynamics starts a seminar by acknowledging that the models are getting harder to believe. It shows up when a review article that should be a triumphant summary of a field's progress reads instead like a careful documentation of everything the field doesn't understand. The galactic center literature has this quality. Read the major review articles of the past 5 years on the galactic center excess, on the S-star dynamics, on the G-objects, on the Fermi bubbles. And you'll find, beneath the careful language and the appropriate caveats, a persistent undercurrent of unresolved tension. The summaries of open problems are long. The sections on future work needed are particularly long. The tone is not of a field that is confident it knows what's happening and just needs to fill in the details, but of a field that suspects the details might not be details at all. This is what quietly panicking actually looks like in science. It's not emergency meetings and raised voices, it's years of increasingly precise observations that keep producing the same anomalies. It's the slow accumulation of things that shouldn't be there but are. It's the growing list of questions that should have been answered by now, and underneath all of it, there's a deeper philosophical unease that doesn't make it into the papers. The galactic center is the closest supermassive black hole to Earth. It is, in a very real sense, our black hole, the one that anchors our galaxy, that has shaped the stellar and chemical evolution of everything in the Milky Way, that has spent 13 billion years eating and growing and occasionally erupting. And despite being the most studied galactic center in the universe, despite the decades of observation and the dozens of telescopes and the millions of hours of computing, we don't fully understand it. The universe's most accessible example of a supermassive black hole and its surrounding environment is simultaneously the most observed and the most confusing object of its type we know. Every time we improve our instruments, we find new things we can't explain. The galactic center is not converging toward a complete picture. It's diverging, spreading out into a richer, stranger, more complicated landscape than anyone expected. That's not panic. That's the opposite of what science looks like when it's approaching an answer. It might be what science looks like when it's approaching something much larger. Chapter 19: The Bigger Picture. Step all the way back, farther than the Fermi bubbles, farther than the Milky Way. Look at the universe as a whole. We know that the universe is made of ordinary matter, atoms, protons, neutrons, electrons, the stuff we're built of, in a ratio of roughly 5% of the total energy content. The other 95% is divided between dark matter, about 27%, and dark energy, about 68%. Dark energy is what's causing the expansion of the universe to accelerate. Dark matter is what holds galaxies and galaxy clusters together. We have no idea what either of these things is, not even close. We can measure their gravitational effects with extraordinary precision. We can predict the large-scale structure of the universe to a few percent using simulations that include dark matter and dark energy. We cannot tell you what particle dark matter is made of. We cannot tell you what dark energy is, whether it's a property of space itself, some kind of field that permeates the universe, or something else entirely. 95% of what the universe is made of is a mystery, not a minor mystery, not a we're pretty sure we know, just working out the details mystery. A fundamental, profound, we genuinely don't know mystery. The galactic center is sitting in the densest concentration of dark matter in our cosmic neighborhood. The anomalies we've discussed, the gamma-ray excess, the X-ray lines, the orbital perturbations, might all be pointing to the same thing. They might be the first faint data points on the dark matter question, the first hints of an answer to the deepest question in modern physics. Or they might be anomalies with conventional explanations that we just haven't found yet. Millisecond pulses and atomic transitions and extended stellar mass distributions and complicated gas dynamics. Things that are hard but not impossible, complex but not beyond our existing frameworks. We don't know which it is. And that uncertainty, at the center of our galaxy, at the heart of what we understand about the universe, is what makes the galactic center not just an astronomical curiosity, but a scientific frontier in the fullest sense of the word. Frontiers are places where the map runs out, where the charted territory ends and the genuinely unknown begins. We've been exploring the galactic center for decades, and we've charted a lot of it. The stellar dynamics, the gas distribution, the magnetic field structure, the energy budget, the history of activity, and the more we chart, the more frontier there seems to be. Conclusion: the center holds 26,000 light-years away. Sagittarius, a star, turns. Gas swirls in its magnetic embrace, heated to millions of degrees, occasionally flaring. Stars orbit in eccentric ellipses, their motions encoding information about the gravitational field, the extended mass, the history of a place that has existed for longer than the Earth. The Fermi bubbles loom above and below the galaxy like enormous wings, the echo of past violence slowly dissipating into the intergalactic medium. Radio filaments stretch perpendicular to the galactic plane, their electrons spiraling in magnetic fields we don't fully understand. And somewhere in the darkness surrounding all of this, invisible and undetectable by any means we currently possess, dark matter, or something that behaves like dark matter, might be slowly, incessantly annihilating, producing a faint glow of gamma rays that our best telescope has been measuring for 15 years, and our best minds have been arguing about for 12. The center of our galaxy is not a quiet place. It is not a simple place. It is not a place that yields its secrets easily or yields them completely. What the scientists studying it are grappling with is something that all great scientific frontiers eventually produce. The sense that understanding one thing has revealed 10 more things that need to be understood. That the closer you look, the more there is to look at. That the universe is not simpler at its centers than at its edges, but more complex, more structured, more surprising. That's actually an extraordinary thing when you think about it. We live in an era where the instruments we've built can detect a gravitational wave produced by two black holes merging a billion light-years away, where we can photograph the shadow of an event horizon 26,000 light-years distant, where we can track individual stars in orbits around an invisible mass and measure the bending of time and light that their motion produces, where we can detect a residual glow of annihilating particles, if that's what it is, from a distribution of dark matter that is invisible in every other way, and we still don't understand what we're looking at. The scientists who are quietly panicking, and the quotation marks are honest, because it's more quiet unease than actual panic, are not panicking because the galactic center is dangerous or threatening. They're not panicking because the black hole is going to do something to us. At 26,000 light-years, even the most dramatic possible eruption of Sagittarius, a star, would produce effects on Earth that range from negligible to very slightly elevated cosmic ray flux after 1 million years. The unease is intellectual. It's the discomfort of rigorous minds confronted with a system that is more complicated than the models, with anomalies that persist across instruments and analysis methods and decades of careful work. It's the specific kind of scientific anxiety that comes from knowing that your field is missing something, without knowing whether what you're missing is a parameter or a paradigm. The history of astronomy is a history of being wrong in productive ways. The geocentric universe was wrong, and being wrong led us to Copernicus and Kepler and Newton. The static universe was wrong, and being wrong led us to Hubble and the Big Bang. The Newtonian universe was wrong at high velocities and in strong gravity, and being wrong led us to Einstein. In each case, the discovery of wrongness was not a failure. It was progress. The progress that only comes from accumulating the evidence that the old framework can't explain and building a new framework that can. The galactic center might be accumulating that evidence right now. The anomalies might be the hints of something new. New particles, new physics, new understanding of what gravity really is, or what dark matter really is, that will eventually force us to build a bigger map. We won't know until we keep looking, and we are looking, with every tool we have, and many tools we're still building. The EHT will produce movies of the black hole shadow. The SKA will find pulsars near the event horizon. The CTAO will measure the galactic center gamma ray excess with 10 times the precision of Fermi. Ixorism will resolve the 3.55 KeV line once and for all. Gravity Plus will track fainter stars in smaller orbits, probing ever deeper into the strong field regime. The galactic center is not done surprising us. The scientists studying it are not done being surprised. And 26,000 light-years away, patient and immense and strange beyond our current comprehension, Sagittarius A waits. Whatever it's hiding at the center of our galaxy, we're going to find it. We always do.